Hello students, we will be dealing with another topic now from the industrial application. We are going to analyze a system from the forced vibration point of view, and the system is going to have masses which are reciprocating also, and they are rotating also. So let us assume that there is a block having a mass m0, and a part of this particular block is undergoing rotation, and that particular rotatory mass is of the mass is m of the rotary portion. And then comes the same old assumption that the rotations are with respect to point O, and the center of gravity is located at a distance of let's say E over here. And we have some stiffness and some damping involved corresponding to the direction in which the oscillations are taking place. In this particular problem, the force, because it happens to be rotating, it is going to have components along the horizontal and the vertical directions, both of them. So in reality, oscillations are present in both directions. They can be present in both the directions. But for the time being, we are analyzing only the vertical component, assuming that the only vertical oscillations are present. And then please note the positive direction of both the coordinate system which have been chosen. The x-axis happens to be positive in the downward direction. And if you notice the position of center of gravity, when the omega is in the negative direction, that is the clockwise direction, the eccentricity is itself moving in the downward direction. So both the directions are oriented along the in the same direction. Anyhow, the total mass happens to be m0, the rotating mass happens to be m, and then since the center of gravity at point E, it is undergoing displacement because of x also, and because of the rotation of E also. So I have x also and rotation of the E also. This is the vertical component of the displacement because of rotation. And since both of them are along the same axis, same downward direction, I have basically added both of them. And then if I find the second differential with respect to time, it gives me acceleration, which multiplied by mass gives me the inertia force. Now coming to the direction of inertia force, since the center of gravity is moving in the downward direction, the inertia force is basically going to be oriented towards the upward direction. So I have taken inertia forces in the upward direction. And then coming to rest of the components, because the mass is moving downwards, okay, the mass is moving downwards, therefore a component given by m minus m0. This is the component of the mass which is undergoing purely linear oscillation, linear movements. Okay, it is not being displaced in the angular direction. It is undergoing purely oscillatory motions. So because the mass is moving downward, this much is going to be the inertia forces which are going to be oriented in the upward direction. And then as the spring is getting compressed, the spring is going to produce additional force in the upward direction, and so is going to be the damping force. And at the last step, you basically add all the forces together. So I have the inertia force as the first term. This is because of the purely oscillating mass. Then I have inertia forces because of the mass which is undergoing both linear and the angular displacements. This is the inertia because of the term m naught. Just a moment. There should be only m and not m naught. And correspondingly, let me correct this thing also. M naught is the total mass, and m is the mass which is undergoing angular. This is what you have assumed over here. The total mass is m naught and rotating mass is m. So this expression is correct. Total mass is m naught, rotating mass is m. Now this is correct. So I have m naught minus m as the inertia because of the oscillating mass. This term because of mass m, which is undergoing oscillation also, and it is going angular motion also, plus the spring force and the damping force. So what I say is that this m multiplied by x dot dot is going to cancel out. What is going to remain is m naught on the left hand side. So this is going to be m naught over here, plus damping term plus stiffness. These are the two terms over here. And then what I see is that this component of the harmonic force is still present, but it is with a negative sign. So therefore, it is going to be transferred to the other side. So this is the entire governing equation. And this is going to be simply m. It is not going to be m naught. It is simply m, which can be taken as the force amplitude multiplied by sine of omega t is equal to the rest of the terms over here. And then we can analyze the same expression on the lines similar to what we have done in the previous cases. Thank you.